Okay, so in this part of the chapter, we're going to see how the quantum mechanical model explains a bunch of stuff. So the chemical properties of elements are periodic because the number of valence electrons is periodic. This explains why in the periodic table, elements in the same column have similar properties because they have the same number of valence electrons. Quantum mechanics explains this because the number of valence electrons and the types of orbitals they occupy are also periodic. So we're going to briefly look at some of the named groups in the periodic table. The first one's the noble gases on the far right side. The noble gases, except for helium, have 8 valence electrons. They are especially non-reactive. Helium and neon are practically inert, meaning they really don't react with anything. And the rest of them don't react with many things at all. So unlike, oxygen that'll react with all kinds of stuff, noble gases react with almost nothing. This is because atoms with 8 valence electrons, or 2 for helium, are especially stable. It's just a very good place energetically. When a quantum level is full, the overall energy of the electrons is lower, and lower energy is more stable. So the noble gases are so non-reactive because their electron configuration is especially stable. So in my weird world of, strange analogies, I think of the noble gases as that in-group of kids in high school, the popular ones that, set all the trends, and everybody else is trying to be like them. You want to be in that group, but you can't, because, let's face it, nobody taking chemistry has ever been in the popular group, right? Well, maybe. I wasn't. So people dress like the in kids, right? The popular group. They have their hair cut the same way. They act that way. I remember watching my kids, dropping them off at high school. It's like, when my oldest was in high school, Hollister hoodies were the thing, right? He had to have a Hollister hoodie. So I bought him one because, I know how that goes. But all the kids are wearing Hollister hoodies because we need to express our individuality, right? All trying to look like the popular kids. So I think of the noble gases as being like the elements that everybody else wants to be like. They're very stable. They don't need to react with anything else. They're just all cool by themselves. Okay, so we'll get back to that idea. The alkali metals are in group 1A. Yeah, question?
So sorry about that. Do you know what chapters relates to and what we have?
Yeah, so this is chapter 9 in the new version. It should be chapter 8.
Okay.
Mm-hmm. Yeah, pretty much everything from chapter 5 on is off by 1 in the older versions. So the alkali metals seem to be on the opposite side of the periodic table from the noble gases, right? But really, the periodic table should be more like a cylinder rather than flat, because like the Earth isn't flat, you can't walk off the edge. After you get to neon, that's not the end of something. You just move around to sodium. And so you can imagine just bending it around just like you could, make the map into a globe, right? So really these are right next to the noble gases. These are very reactive elements. They all have 1 valence electron. They can attain a noble gas electron configuration, have electrons that look like the noble gases by just losing 1 electron. And so they will do this very readily. So they react to lose that S1 electron. So here we have the last term in the electron configuration, 2s1, 3s1, 4s1. If lithium loses that 1 electron, it goes from 3 electrons to 2 electrons. It has the same number of electrons as helium. That makes it very stable. Does it turn into helium? No, it doesn't. because the number of protons doesn't change. So the nucleus, the number of protons is like your soul, your personhood, right? You can't change who you are, but you can change what you look like. So the nucleus is on the inside, the electrons are on the outside. You can change how many electrons an atom has, but you can't change who it is outside of nuclear chemistry. So these guys I see as like, the kids, that they're pretty cool, but mom forced them to wear this dorky hat because it was cold and she's worried about them getting an ear infection or something. So they're like, and they go off to school with this stupid hat on, this one extra electron, and what do? They take it off as soon as they can, right? So these elements all lose one electron very readily. They'll react with almost anything that'll take that electron, okay? Yes?
Is there an easy explanation as to why hydrogen is not paired with the
Yeah, so why is hydrogen not in here? Well, hydrogen isn't a metal. So technically, even though hydrogen is in group 1A, technically it's not an alkali metal because it's a gas. So, but for the most part, when we're looking at charges and valence electrons, we can just look at helium along with the rest of them. But if helium loses an electron, it does not have a noble gas electron configuration, right? Then it becomes a bare proton, and that's a whole nother thing. So this is why the alkali metals form +1 ions. We learned that back in chapter 3, right? Just to predict charges based on position in the periodic table. Well, now we can see why they do this. So the group 1 elements form +1 ions because by losing that one electron, they have the same electron configuration as the noble gas, and that is lower in energy and it's more stable. That make sense? On the other side of the noble gases is group 7A. These are called the halogens. The halogens have one less electron than the noble gases. So they're also really close to having that 8 valence electrons, which is especially stable. And so what do? They're going to gain one electron whenever they can. So they're also quite reactive. So we see here, like with chlorine, chlorine's electron configuration ends in 3s2, 3p5. If we give it one more electron, that will be 3p6, and it will be the same electron configuration as argon. Chlorine doesn't turn into argon when it becomes a chloride ion, but its electron structure is identical to argon. Okay? So that's why the halogens form -1 ions, because that gets them a noble gas electron configuration, makes them more stable. So we learned in chapter 3 that there are a lot of metals and nonmetals that only form a single ion, and that those charges are predictable based on position in the periodic table. We learned that group 1A forms +1, group 2A +2, and group 7A was -1, group 6A was -2, and we were just counting backward from the noble gases. The reason they form ions with those charges is because that's what gives them a noble gas electron configuration. So this is a figure from the textbook, and we're in the 5th edition now, and they still have the period numbers wrong. This is the first row that they're showing, but that's not period 1. Period 1 is up here where hydrogen and helium are. One of these days, I need to carve out some time and email them about this, but it's just not been real high on my priority list. But here we can look at what's going on. So the noble gases are over here. They don't form ions because they're cool all by themselves. They don't need to react or anything. They're just like in a sweet spot, right? Here are the halogens. These all form -1 ions because that's what happens when you gain an electron. By gaining an electron, they have the same number of electrons as a noble gas. Group 6A, these all form 2 minus ions. They gain 2 electrons because when oxygen gains 2 electrons, it has the same number of electrons as neon. On the outside, the electron configuration is the same. It doesn't become neon. It's just changed what it looks like on the outside. So you can color your hair, you can get tattoos and piercings, you can wear all kinds of different clothing, masks, whatever. You can make yourself look like somebody else, but can you become someone else? No, you can't. So these elements can have the electron configuration of another element, but that doesn't change them into the element. Nitrogen would gain 3 electrons to have the same, and I don't know why they do this either. They leave phosphorus off of here. Phosphorus does that as well. And then looking at the metals over here in group 1A are going to lose 1 electron to be like a noble gas. Why doesn't sodium gain 7 electrons to become like argon? Well, it's got a choice. I could gain 7 electrons, or I could lose 1. What's easier? It's easier to lose 1, right? So the metals lose electrons. Group 2A metals lose 2 electrons. Because they have 2 valence electrons, they need to get rid of those valence electrons because under that valence shell is a completely full shell. So if we go to the hotel analogy, the valence electrons are the people staying on the highest occupied floor of the hotel. And so sodium has 1 person staying on the 3rd floor, and if that person leaves, then there will be 10 people left, and the 2nd floor will be full, just like neon. And so that's lowering energy. Magnesium would lose 2 electrons. Over here, aluminum will lose 3 electrons because it's still harder to gain 5 than to lose 3. And then we see for group 4 here, we're not listing any predictable ions. Those guys are right in the middle. It's like I have to gain 4 electrons or lose 4 electrons. Either way, it's just too hard, so I'm not going to do it. They don't form ions for the most part. They do other things to become like the noble gases, but they don't form ions. Any questions? And then these guys in here are another story. Yes? Yep. Yep. Yeah, so over here, the nonmetals are going to gain electrons to get a noble gas electron configuration or to get 8 valence electrons, and the metals are going to lose. And the metals go all the way over to, let's see, aluminum. This is the line that divides the metals and nonmetals. So we can look at, well, what's the closest way to get to a noble gas? Well, I can go 2 squares over here. That means gaining 2 electrons. For this one, it's moving 2 squares to the left, which is losing 2 electrons. Or we can remember that non-metals and negatives start with N. Non-metals form negative ions, and metals form positive ions. Any other questions? So what about the electron configurations of these anions or cations? Look at the anions first. So the anions form when the nonmetal atoms gain enough electrons to have 8 valence electrons. So what that means is that the s and p orbitals of the valence shell are full. So the sulfur atom has 6 valence electrons. This is its electron configuration. In order to have 8 valence electrons, so let's highlight the valence electrons. Those are the ones in the highest level. So the 3rd floor has people on it. That's the valence floor, the 3rd principal level. We want 8 electrons up there. We've got 6. We need to add 2, right? So here we've added 2, so it's 3p6 at the end. But that changes the charge. because in a sulfur atom we have 16 protons and 16 electrons. And so we've got 16 positive charges, 16 negative charges. Overall, it's neutral. Here we still have 16 protons, but now we have 18 electrons. And so we've added 2 negative charges, and so this has a -2 charge, right? This electron configuration is the same as for argon. The electron configuration isn't saying anything about what's in the nucleus. It's just saying, where are the electrons? Any questions? For cations, we're going to lose electrons, and the atom is going to lose all of its valence electrons. This process is always endothermic. It does come at a cost because, well, if it didn't, then we'd never see a sodium atom because the electrons would always just fall off spontaneously. There is a cost involved, and energy has to be put in, but there's other energy benefits that make up for it later. So this is always endothermic. So here's the electron configuration for magnesium. Where are the valence electrons? The 3s2. Remember, the valence electrons, we're looking for the highest principal quantum number. These large numbers represent the quantum number, principal number, or the floor in the hotel. What's the largest one? And then all the electrons in that level, 3s, 3p, however many, are the valence electrons. So magnesium is going to lose those 2 electrons. They're going to leave. And so then it has this electron configuration, 1s2, 2s2, 2p6, which is the same as the electron configuration for neon. In this ion, where are the valence electrons? They're still the highest occupied level. In the hotel, floor 3 emptied out. It's empty now. Those people left. So now the highest floor that has any electrons on it is 2. And so these become the valence electrons. And so magnesium cation has 8 valence electrons. We don't say it has 0. This is like, if you think of these, it's always hard to decide how to draw this. The Bohr model is kind of useful here. So magnesium, we've got 12 protons here in a nucleus. And then just using the Bohr model because it's easier to draw. In the first level, we have 2 electrons, and in the second level, the S and the P, we've got 8 electrons. And then in the third level, we have 2 electrons. That's for the atom. So if you use your imagination, that looks a little bit like an onion, right? And onions have layers, right? And that makes us think of Shrek and the donkey. Yeah, that was a great movie. Onions have layers. So this outside layer of the onion, this outside level of the atom, isn't full. It's just a partial level. It's like you get an onion, and it's like, well, there's part of this layer is there, but then the rest of it's gone. And so, well, let's just knock off that, and now we've got this nice smooth onion. We'll take this and we'll chop it up and do things with it, right? So what the metals do is they've got this partial layer up here, and it's easier to just lose the layer. What's underneath the layer? A full, intact layer of onions, right? So we're taking off this partial one, and underneath we have a nice full one. So we lose those 2 electrons, and now we've got 8 valence electrons, and it's very happy. Yes?
So we're saying that this one is endothermic. Can we say that the electron configuration of the ion is
So when an anion forms, we'll get to that later in this chapter. That's called electron affinity, and sometimes that's exothermic and sometimes it's endothermic. That's why they didn't mention it yet. Any other questions?